So hello everyone, my name is Anthony Jr. and today we are going to create a clustering model for our laboratory activity. So first that we need to do is uh, retrieve the dataset which is named water potability. So let's run it. So here's our dataset. So as we can see, we have 3,276 observations with 10 regular attributes. So each attributes indicates the chemical or the characteristic of the of the specific body of water. So first is the pH value. So pH value is an important parameter in evaluating the acid-base balance of water. So it is also the indicator of alkaline condition of water status. So current investigation ranges were 6.52 to 6.83, which are in the range of WHO or World Health Organization standards. So hardness is the mainly cause of bicalcium and magnesium salts. So these salts are dissolved from geologic deposits through which the water travels. So the length of time water is in contact with hardness producing material helps determine how much hardness there is in raw water. So next is solids. So solids are the total dissolved solids. So water has the ability to dissolve a wide range of inorganic and suborganic minerals or salts such as potassium, calcium, sodium, bicarbonates, chlorides, magnesium sulfates, etc. So these minerals produce unwanted taste and diluted color in the appearance of the water. Next is chloramines. So chloramines uh, are chlorine and chloramine are the major disinfectants used in public water systems. So chloramines are most commonly formed when ammonia is added to chlorine to treat drinking water. So chlorine levels up to 4 milligrams per liter are considered safe for a drinking water. Next is sulfate. So sulfates are naturally occurring substances that are found in minerals, soil, and rocks. So they are present in ambient air, groundwater, plants, and food. So the principal commercial use of sulfate is in the chemical industry. So sulfate concentration in seawater is about 2,700 milligrams per liter. So it ranges from 3 to 13 milligram per liter in most freshwater supplies. Next is conductivity. So for conductivity, so pure water is not a good conductor of electric current, rather it's a good insulator. So increase in ions concentration enhances the electrical conductivity of water. So the amount of dissolved solids in water determines the electrical conductivity. So the electrical conductivity of the water actually measures the ionic process of a solution that enables it to translate. Next is organic carbon. So organic carbon or the total organic carbon in source waters comes from decaying natural organic matter as well as synthetic sources. The next is trihalomethanes. So the THMs are chemicals which may be found in water treated with chlorine. So the concentration of THMs in drinking water varies according to the level of organic material in the water. So the amount of chlorine required to treat the water and the temperature of the water that is being treated. THM levels up to 80 ppm is considered safe in drinking water. Next is turbidity. So the turbidity of water depends on the quantity of solid matter present in the suspended state. So it is a measure of light emitting properties of water, and the test is used to indicate the quality of water discharge with respect to colloidal matter. colloidal matter. Then next is potability. So potability is a binary label. So this is our target label. So 0 and 1. So 0 means the water is not potable or the water is not safe for human consumption. And 1 means potable, which means it is safe for human consumption. So we have now imported our data. Next thing that we are going to do is we are going to fill the missing values because as we can see, we have missing values in our data set. So in order to do that, we will just type replace missing values. So we will use the average or the mean for that. So we will run this now. So as we can see, we have no more missing values. The next thing to do is we are going to set rule for the potability as our label. So label run. So here we are now. So we have already one special attribute and 9 regular attributes. Then next is we are going to normalize our data using the normalize operator. So all, then Z transformation. So there we go. Then next is we will build now the clustering model. So let's look for clustering and we will use k-means. So by default it is 5. So we can change that later on, but let's try for now 5 and see the result. So this is the result or the predicted cluster for each of them. So as you can see, we only have 2 variables. So we will change the k to 2. Then let's look at it at the cluster model. So as we can see, we have 1,436 items for cluster 0 and 1,840 items for cluster 1. So let's look at the folder view. So first is cluster 0. So cluster 0 are kind of mixed. So we have here a data that has a potability of 1. And see here, we also have data that has a potability of 0. Then let's look at the cluster 1. So yeah, it is kind of mixed. Then we have potability with 1. So now let's try to check the performance first using the cluster distance performance because we have a cluster model. And so move this first. And then then connect the cluster to the example, and then let's also connect the cluster here to the result. You can see a graph. So this is the cluster, but our cluster model. And centroid table. So for cluster 0, these are the attributes and the value for each attribute, and this is for the cluster 1. So let's look at the uh, performance. So average within centroid distance is negative 8.266, which is quite high. But as we can see for cluster 0 and cluster 1, it is almost the same here. Then Davis Bolden is kind of far with negative 3.211. So it's kind of high because it may be because the data have some uncertainty or irregularity inside. So let's try to remove the normalize because at first we can see that our data is have a already kind of normalized value. So let's try to remove that and see what will be. So, so it became higher, but if we look here at the Davis Baldwin, it have a low index, which means uh, 0 to 1 is good for this. Then, so let's bring it back. Yeah, and there we go. This is our clustering model. So that's all, and thank you.